In this lecture, we're going to talk about power transmission and how we get electricity, which by that we mean a voltage source, from one location to another. Now, almost all the electrical energy sold today is in the form of AC because of the ease with which it can be transformed from one voltage to another. In the US, we use 60 hertz as the sinusoidal, how many cycles per second the voltage goes from a max to a minimum back to a maximum again. As we said before, in homes that we are used for the most part for our appliances, we use that at 120 volts, which we said was the average voltage of the sine wave. It is not the peak voltage. The peak voltage is about 170. But this is generally what we have. Now, one of the reasons why we transmit the electricity in high voltage is that power is equal to current times voltage. I think we discussed this in the previous chapter, but we can either deliver, if we want a lot of power, we can either deliver it as a lot of voltage or we can deliver it as a lot of current. The problem with delivering as a lot of large currents is that in wires, this produces heat and energy loss. So the power that is transmitted a long distance away is going to be quite a bit less by the time it reaches your home. So here at the bottom, we've got our power generator. We have our voltage lines coming out. The voltage gets stepped up to voltages as high as 750,000 volts for long distance transmission. And as a result, I can trade off at any given point along the line a voltage for current. And therefore, if I transmit voltage, then I will not have the heating and energy losses that are caused by current. Now, the power generation is typically at about 25,000 volts when it leaves the station, and it's then stepped up to 750,000 volts for its transmission, and then it is stepped down in stages at substations as we get closer and closer to the home. Here you can see the voltage is initially rising, which shows the wires going to a higher level. They gradually go to a lower level, and then this is a substation, and then the substation will deliver that at a lower voltage as it gets close to the consumer, which is the home. So voltage is stepped up after leaving the station, and then stepped down at substations until very close to home. It will be delivered as either 120 volts AC or 220 volts. Now, most home appliances use 120, but a noticeable exception to that is the air conditioner, which is a very power-hungry device, and they run at a higher voltage, as well as high current. So high meaning anywhere from 10 to 15 or 20 amps. And industrial applications, such as buildings and high-rises, have substations that deliver voltage at about 440 volts. So how do we get the voltage to go up and down from the location of the power plant to the usage for the end user? Well, we use what's called transformers. And transformers can either transform high voltage to low voltage, or, which is not stated here, it can also transform a low voltage to a high voltage. So when we go from a high voltage to a low voltage, that's called a step-down transformer. When we go from a low voltage to a high voltage, that's called a step-up transformer. The way in which we do that is by taking a certain number of windings around a piece of iron, which you can see right here. The iron conducts the magnetic field generated by the coils, and we can show that the voltage in the secondary coil, which is over here, is to the right, is different, or can be, let's say, higher or lower than the voltage in the primary. So the primary voltage, which is given by VP here, can be transformed to a lower voltage in the secondary winding by using a smaller number of loops in the secondary winding than you have in the primary winding. So by adjusting, if this ratio is less than 1, then it becomes a step-down transformer. And if this ratio is greater than 1, it becomes a step-up transformer. This is the way in which we can change the voltage. And as a result, because energy is conserved, when the voltage is, for example, transformed to a lower value, then the resulting current increases as a result. Because remember, power is voltage times current, so if I step down the voltage, I step up the current. Again, same message here, same equation. Now, typically we have that both are wound on a common iron core, so the magnetic field of the primary passes through the secondary. So here you have the primary windings, and here, down here, you have the secondary windings, and they share a common core of iron to transmit those effects. But the important thing is that this equation only works when you're using an alternating current or alternating voltage in one coil to induce alternating current and voltage in the second coil. So we have to use the property that the voltage is changing with time. As we've said just briefly before, the transformers can either step up or step down voltage depending on whether the number of windings in the secondary is greater than the number in the primary, or vice versa. And we do that simply by changing the number of coil windings or loops that are made around the iron. And just states it another way, this was taken from the book's example. Primary voltage divided by the number of primary turns equals the secondary voltage divided by the number of secondary turns. And that's the same as the equation that we've had in the previous slide. So transformer transfers energy from one coil to another. It is a rate of energy the rate of energy transfer is called the power. And the power that's applied into the primary coils will be equal to the power into the secondary coils if there are no other losses. And so for an ideal system, we can say that the voltage times the current in the primary coils is equal to the voltage times the current in the secondary coils. And so stepping up the voltage means stepping down the current, stepping down the voltage means stepping up the current. Transformer transfers energy from one coil to another. Example, voltage stepped up before leaving the power station. The voltage is stepped down near the cities or close to where we are going to actually use it. And then it's stepped down again before being supplied to your home. So we have various stages in which we step up or step down, and the picture of a transformer is shown here on the right side, which consists of these windings around an iron core. How would we answer this question? A step-up transformer, an electrical circuit, can step up voltage, it can step up energy, it can step up both the voltage and energy, or it does neither one. Well, we know that D is not correct, and the correct answer is A. Stepping up energy violates conservation of energy. So if we could step up the energy, we could generate a lot of electrical power, without doing hardly any work at all. And of course, that's simply not how the world works. It can only step up the voltage in this kind of scenario. Another question you can ask yourself: an efficient transformer in AC electric circuit, does it change the current? Does it change the energy? Does it change the power? Or all of the above? Well, we've just answered that a transformer cannot change the energy. It cannot take a given amount of energy on the input winding coil and translate that to a higher electrical energy on the output coil. So if that is true, then the rate at which the energy is being supplied cannot be any different than the rate at which the energy is being transformed. So power is energy per unit time. Power cannot change as either. So the only one really left is the current, which is kind of what we had talked about earlier, in that it's the current that, since the voltage is changing with a step up or step down transformer, then the current will also change as well. So then one of the last things to talk about is self-induction. Current carrying loops in a coil interact not only with loops of other coils, but also with loops of the same coil. Each loop in a coil interacts with the magnetic field around the current in other loops of the same coil. And this is called self-induction. When the switch is open, the magnetic field of the coil suddenly collapses, and this sudden change can induce a very high voltage because we are changing the magnetic field very, very rapidly. So each loop in a coil interacts with the magnetic field around the current in other loops of the same coil. So in other words, every loop in that coil is generating a magnetic field that interacts with the other currents and generates a magnetic field that interacts with the currents in the other loops. And this is called self-induction. Field induction states that an electric field is induced in any region of space in which a magnetic field is changing with time. And it's a statement of Faraday's law, but there's also a counterpart to Faraday's law, which states that a magnetic field is induced in any region of space in which an electric field is changing with time. So these have complementary effects, that you can create an electric field by making which is voltage in a wire, by making a magnetic field that changes with time, or I can generate a magnetic field by making an electric field that is changing with time. So these things are complementary with each other. And this leads to the idea that light waves, and also we can say radio waves, are produced by the mutual induction of electric and magnetic fields. So the changing electric field generates a magnetic field, and the changing magnetic field generates the electric field. And here we see in an electromagnetic wave, such as what we get with light or with radio waves, that every point along this axis, this is a moving wave. This whole wave in red and blue is moving in the positive x direction to the right, and it is moving at the speed of light, which is 3 times 10 to the 8th meters per second. And that's true whether this is a radio wave or it is a light wave, because they are both oscillating electric and magnetic fields. And these fields propagate away from their source, which can be an antenna if we were generating, for example, radio waves at a fixed speed, regardless of their frequency. This interaction between electric and magnetic fields gives rise to radio waves, and the first radio wave that was generated this way by placing a voltage on an antenna wire was the first demonstration of this was by a scientist named Marconi, who in 1903 generated a radio wave that got transmitted from Europe to the North America, showing that we could transmit signals across the Atlantic Ocean in less than a second. This was a very important part of the development of technology in the early 20th century. Application of Faraday's law, activation of traffic lights by a car moving over underground coils of wire. This will trigger the change in traffic lights. A triggering security system at the airport by altering the magnetic fields in the coils as one walks through. Scanning magnetic strips on back of credit cards. Recording of sound on tape. Electronic devices in computer hard drives. And of course iPods. All of these use Faraday's law of magnetic induction to generate their signals. Self-check question for you. More voltage is induced when a magnet is thrust into a coil quickly, slowly, or does not depend on how quickly a magnet is thrust into a coil. Well, we've had a lot of discussion about that today, and so hopefully you're able to choose the right answer. The voltage generated on a coil is directly related to how quickly the magnetic field changes. So by pulling a magnet out of the coil quickly, then I'm making a rapid change in the magnetic field in the coil, and that will then generate a higher voltage as a result. So answer A must happen more quickly. Further checks that we could talk about. Another question, not only is voltage induced when a magnet is thrust into a coil of wire, but something else is also induced. Is it current? Is it energy? Is it power? Or none of the above? When voltage is induced when a magnet is thrust into a coil of wire, then which of the following is the following? Well, let's take a look. Looks like the answer is current. We could have suspected that, of course, because anytime we induce a voltage across the ends of two wires, then there will in fact be a current. And that current will be there we know that from Ohm's law, that voltage equals current times the resistance of the wire. So certainly current is going to be induced. The commentary given by your author is that energy or power, which are conservation of energies, cannot be created because you have to supply the energy to induce this voltage. So energy can be transferred, but it cannot be created by induction. And I think that's what makes this the right answer. We can supply the energy by vigorously moving the magnet in and out of the coil, but we cannot, and we do get electrical energy as a result, but it's only because we've supplied mechanical energy and we have not created it. So that one looks pretty good. Another question we could look at, the resistance you feel when pushing a piece of iron into a coil involves repulsion by the magnetic field you produce from current generated in the coil, the energy transfer between the iron and the coil. It is a result of Newton's third law. It is the resistance you feel is due to resistance to the domain alignments in the iron. Well, I'm going to exclude the last one right away, resistance to domain alignment in the iron, because we can assume that this magnet is already completely magnetized as a permanent magnet, and therefore the domains are already aligned. They do not become unaligned as a result of pulling it in and out. So we can go through it and look at the result. This one is a very much harder one to answer, so I'm going to answer it for you. That the resistance you feel when pushing a piece of iron into a coil involves repulsion by the magnetic field that you produce by the current generated in the coil. Now this is another way that we express a law that is derivable or is a corollary of Faraday's law, which is stated as Lenz's law, which says that the induced voltage gives rise to a current in the coil, and that current that is created in the coil produces a magnetic field that acts against the motion of the iron that you are thrusting. That is why electricity generation requires work. Even if you have no resistance or no friction in your system at all, you still have to do work in order to generate that electricity. There's no system in which we can do it otherwise. So, congratulations. You have now finished the physics lectures for the entire course, as well as electricity and magnetism. One thing that you need to be sure to do is to finish the problem set in chapter 25 that you can find on Mastering Physics and begin preparing for the final exam. So at this point I will stop, and if you have questions we can talk about it during office hours. Thank you very much.